Right, so first of all, thanks to the organizers. It's great to be here in this nice sunny place. Um, I'm going to be talking about insights into structure growth in the early universe from CMB lensing and kSZ today. And as you might suspect from the title, this is really two talks that have been shamelessly shoved into one. In the first part of the talk, I will discuss what we can learn from new CMB lensing measurements about the growth of structure and about other things like tensions. And in the second part of the talk, I will just briefly discuss what we can learn about primordial non-Gaussianity from kSZ measurements, a field that's just taking off now. All right, let me start with the first topic, and obviously feel free to interrupt at any time if you have any questions. I think this audience needs pretty much no motivation for why studying the growth of structure is interesting, and why the sort of long redshift lever arm test that we usually do is particularly compelling, right? I mean, you all know that we can do a test of our standard cosmological model where I fit a lambda CDM cosmology to the CMB power spectrum, which mostly, but not exclusively, probes redshift 1100. And then I can predict sigma 8 at low redshifts. I can then go and I can compare the direct measurements of sigma 8 from lensing and clustering and other probes with this prediction to look for any discrepancies, because such discrepancies would indicate new physics, whether it's dark matter physics, dark energy physics, gravity physics. So this is a generally extremely well-motivated thing to do, and it'll get more and more interesting with better and better data. But of course, you also know that in recent years, there's been, for better or worse, more motivation for studying the growth of structure, namely the well-known sigma 8 and S8 tension between the sort of predicted values based on CMB power spectrum fits for sigma 8 or S8, which is just closely related, and what we directly measure from weak lensing and other probes at low redshift. So what's notable here is that there are several different measurements that at least were 2 to 3 sigma low. The question is this still an interesting problem? There have been significant developments. In particular, the KIDS legacy release is now in much better agreement with Planck, and so one could debate how much should we still worry about this. But nevertheless, measuring growth of structure in general is a really interesting problem, and it is really well motivated, and this motivates measurements with CMB lensing, which have several advantages. First of all, they are very reliable and entirely different from all of these probes, at least in terms of their systematics. They don't rely on galaxy surveys, they don't rely on Planck, and so they're very much a different picture. And they also probe very different redshifts and scales. So if you actually believe that this is a sign of new physics, you want to probe physics in all the different regimes. All right, lensing is also really important, and one of our best ways of getting the neutrino mass in combination with BAO and primary CMB constraints. So CMB lensing helps to probe the neutrino mass both via the suppression of structure and because it informs our measurements of the background matter density, and both of these contribute to a tight measurement of the neutrino mass. Now this is an area which has arguably gotten more interesting, unlike the S8 tension in recent years, where the constraints from DESI have come in, as you all know, sort of surprisingly tight, as we heard about from Dragan. And it's worth thinking about whether this is actually telling us something interesting or whether it's all consistent and fine. The one point I'll make immediately, though, is there were some claims that this has nothing to do with lensing. That's certainly not true, in the sense that if I marginalize over the amplitude of lensing in both CMB power spectrum and 4-point function, the constraints are completely destroyed, right? They become this dashed line here, and you're completely consistent with minimal mass, and they're no problem. So in some way, in this combination, CMB lensing is adding a lot of information. All right, so that motivates measuring CMB lensing. And I think this audience knows what CMB lensing is. It describes the fact that as the photons of the CMB travel through the universe, they're gravitationally deflected by the entire mass distribution, including the very high redshift mass that we have difficulty accessing otherwise. And the deflection remaps the CMB by an angle which is given by grad phi, where phi is the observable that we use, the lensing potential. Now, how do we measure this lensing potential? Well, what most of us are still doing is measuring it with a quadratic estimator, which just involves looking for mode coupling, correlations between two different modes that used to be independent before they were lensed, and summing over all the different pairs of modes to get an estimate of the lensing potential. So this is what we actually do in practice. We just compute an integral summing over pairs of modes with some weights that I'm not talking about here. Let me try to give some intuition for what this is physically doing. Like, what is this quadratic estimator doing? What is the intuition? You can have an intuition for this, at least in some regime, is measuring a position-dependent power spectrum. Okay, so in each little region of sky, you measure a power spectrum, and you look at how that power spectrum is modulated by magnification and shearing compared to the standard object. So just like in galaxy lensing, I have the shape of a galaxy on average. Here I have the average CMB power spectrum. But if I look in a region where the CMB has been magnified, then that power spectrum will be shifted to larger angular scales than the average. And you can also look at a similar effect where it's sheared, right? There's a two-dimensional power spectrum, it'll be distorted. And so in this way, you can go from a map of the CMB or the polarization to maps of the CMB lensing. Right? And obviously, if we want to do quantitative cosmology, if we want to measure the growth of structure, look for new physics, check for tensons, measure the neutrino mass, we want to measure a power spectrum of this lensing, the lensing power spectrum CL55, which is directly sensitive to sigma 8. More specifically, it's sensitive to S8 CMB lens, which is sigma 8 times omega matter to the 0.25. And just to emphasize the nice complementarity of the CMB lensing power spectrum with other probes, right? I think it's clear to everyone that even though we always plot structure probes as all measuring sigma 8 or S8, they're really probing the growth of structure and the matter power spectrum on different redshifts and on different scales, right? So, if I plot what redshifts and what scales different probes access, you'll see that, CMB lensing is quite unique in that it not only probes a pretty wide range of scales, increasingly pushing towards smaller scales, but it kind of is unique in accessing this really high redshift range above redshift 2 and 3, with a tail that stretches all the way out to sort of redshift 5 and 6. So, this is quite powerful and unique, and it's also nice if you want to find some new physics via scale dependence or redshift dependence, you can compare with CMB lensing to get a redshift or scale lever arm. So yeah, I think that hopefully has motivated why we'd like to measure CMB lensing. Are there any questions so far? Comments? Presumably a lot of this was well known. All right. What I'm going to do next is I'm going to do a lightning review of the recent ACT-DR6 results from 2024. And then I'll talk about new lensing results that came out this year and what's in the works now with ACT and SO. All right, so quick review of ACT results and then on to new things. So the Atacama Cosmology Telescope, just for those of you who don't know about it, is actually a former telescope. It's very sad, it doesn't exist anymore. It was taken off the mountain, is now in a museum. But the final ACT-DR6 data set is still an amazing CMB data set. It's large sky, high resolution, low noise, and fantastic for measuring lensing. And so my students, Frank Chu and Neil McCran and Dongwon Han and my great collaborator, Matt Mandavacero, we put out fairly recently this ACT-DR6 lensing measurement and lensing power spectrum. Without further ado, let me just tell you about it. I'm going to start by just showing you one of the headline results, which is mostly nice because it's really pretty. The ACT-DR6 CMB lensing mass map, right? So this covers a quarter of the sky. And what you're seeing here is the lensing convergence, which is directly proportional to the mass density and projection. And since it's CMB lensing, it's a huge, the integral extends over a really wide range of high redshifts. This map has been filtered, so these are, you're suppressing noise. These are real structures in the mass and the dark matter on the sky. It's a very high fidelity map. It has something like twice the signal to noise per mode compared to Planck. And yeah, so we're mapping the dark matter on large sky. Just to show off this map a little bit, let me zoom in to a small cutout. Just look at the sort of fluctuations in the projected mass. It's easy for me to say that this is high fidelity, but there's a nice trick we can play where we compare the dark matter seen in CMB lensing with a galaxy tracer coming from similar redshifts. And if this really is imaging the large scale structure, we should see a clear correlation. And hopefully you agree that this is somewhat correlated, right? So what you see in these contours is the strength of emission from dusty galaxies. In other words, the infrared background. And it's not surprising that given that these are coming from similar redshifts, the kind of luminous objects trace the underlying dark matter, but it's cool to see that this actually works by eye. And it's a nice illustration of the fidelity of these maps. But of course, if we want to do quantitative cosmology, we need to measure the CMB lensing power spectrum. It's not quite as simple as just squaring this lensing map because, it comes from a quadratic estimator. Suddenly you're generating a 4-point function. There's a bunch of disconnected biases. Yes. Yep. Yes, so, but the same is true for the infrared background emission. It also comes from a really wide range of redshifts, which matches the CMB lensing origin actually quite closely. It's not perfect, but they're correlated around 80%, these fields. So it's the tracer you want to use if you want to make this kind of picture, because it really comes from very similar redshifts. Okay, yes, we want to measure lensing power spectrum. We've known how to do this for some time. What's hard, though, is really convincing yourself that you believe your measurement, especially at the kind of percent level. And so, what you do if you're a CMB lensing person is you make a measurement and it looks cool, and then you spend 3 years of your grad student's time, not your own time anymore, but just doing hundreds and hundreds of null tests, right? So the vast majority of the work goes into just checking that you get consistent lensing power spectra in different frequencies, in temperature versus polarization in different parts of the sky, in different scales, et cetera, et cetera, et cetera. So that took the vast majority of Frank's time and our time. And initially, all these consistency tests, so what you're seeing here is sort of consistency of the amplitude of lensing, which is like an overall factor. Initially, this all looked really bad when we started, and there were 2 main problems that we needed to overcome. And the first problem is what I would call the noise problem, and the second problem is the foreground problem. So let me just talk about those 2 in turn. Yes? Right, so I mean, once you get the output of the quadratic estimator, then you effectively measure pseudo-CL power spectrum. But because it's a 4-point function, you just care about the non-Gaussian part, you need to subtract off the disconnected part of that 4-point function. So what's used there is a sort of realization-dependent bias subtraction that comes out of a maximum likelihood analysis with the Edgeworth expansion and involves combinations of simulations and data. So that's really a key step. And then in addition, after subtracting off the leading disconnected part, there's some higher order biases that get computed and subtracted. There's a simulation-based correction that's applied that's very small, but sort of, sort of between percent and 10%, depending on what you're talking about. And then we get to our final result. What was that? Well, so, yeah, right. So the way the quadratic estimator is derived, it basically just isolates the leading contraction, the first order contraction between lensing in here, in these 2 temperature legs. If I now form a 4-point correlation function, I get sort of accidental other contractions of lensing. Like, if I have 4 fields, I'll get the first field the lensing in the first field accidentally contracting with the lensing in the 4th field. So there's, at the same order, there's another order CL5 correction, but it's suppressed because the filtering is not optimized to get that. So that's, it's not just the disconnected part. There's the same order correction that gets modeled. It actually gets forward modeled, usually, not subtracted. Yeah? Yep. Mm-hmm. Yeah, so I guess the thing to be a little bit careful of here is that the scales that we reconstruct the CMB from are not the same scales as we measure the lensing on, right? The lensing is a modulating field, which is generally larger scales than the sort of small scale CMB fluctuations that we use to measure it, right? I mean, you can sort of, so here, right? So, basically here you can see I can measure L of 100 in the lensing by comparing L of 2000 and 2100 in the CMB. Yeah, yeah. I think this is something that's not always appreciated. So this is changing the CMB source L, right, which is often a test of either foregrounds at high L or instrumental things like transfer functions at low L. But we find stability to both of these changes. Any other questions? Yeah, feel free to. Okay, let me talk about the problems that we had to overcome in this analysis before I talk about new results. The first problem is what I would call the noise problem. So if you have a nice lensing pipeline, you spend a long time building it, and you take a map with just noise and you run it through that pipeline, you better get 0, right? You would hope. But when we took noise from our data, which we can get by differencing observations taken at different times, instead we got this horrible green curve, so not at all null. And so about a year of our lives was spent figuring out what was going on here. So it turns out what was happening was that even though the lensing pipelines are pretty robust to simulating your noise wrong, if you're very wrong, they break down. So this disconnected bias subtraction is robust to first order in errors in your covariance, but not higher ones. And so what was happening is that the ground-based noise in the Atacama was just very complicated. There's atmospheric noise, the scan pattern is really complicated. We did a lot of work to get our simulations to be good. They're good enough for error bars, but the bias subtraction was breaking down. So we had to sort of come up with and implement a new way of measuring lensing, which is conceptually pretty straightforward. Basically, I use 4 CMB maps with independent noise, and I construct sort of the generalization of a cross correlation to a 4-point function. Okay, so I basically measure a cross correlation 4-point function where I never repeat the same data taken at the same time twice. And then all the noise sort of cross correlates away, and I don't have any noise contribution to my 4-point function. Right, so the difficult part is getting this to run fast enough, but eventually figured it out, and that solved all of these noise problems. Everything passed, everything looked nice, as shown here in blue. The second challenge was how to deal with extragalactic foregrounds. So those are, I would say, by far the main thing that you have to worry about for CMB lensing analysis, right? It's generally really, really robust in the sense that you know exactly what redshift the CMB like that. We really understand the properties of the linear CMB source extremely well. We're on very large scales, so we don't care about baryonic effects, at least until the next generation of experiments. We don't have intrinsic alignments. I mean, yeah, it's generally an easy problem, but foregrounds are the one thing that we do have to think about. But even they are not so bad. The story there is that the CMB is not just lensed, but it's also scattered by SC clusters, which you can see here in blue in the CMB map. And the CMB is also joined by emission from galaxies. Like here I have dusty galaxies. And these are also some source of sort of non-Gaussianity, and they will, to some extent, contaminate your lensing. But even if you do basically nothing, it's kind of a percent level problem, few percent level. And you can understand why that would be, right? These dots don't really look very much like lensing. So there are two things we can do about this. Actually, one note is that if you don't do anything and you have foregrounds in your map, counterintuitively, they actually don't add to your lensing, they lower your lensing usually, right? It's because they're correlated foregrounds. I'm happy to talk more about why that is, but maybe worth bearing in mind if you think about lensing being high. Okay, but yeah, they don't do very much, but at the percent level, we need to suppress them further. What we did is we had two different approaches. One of them is sort of a geometric approach, whereby we modified the estimator to not be sensitive to Poisson distributed sources with a certain profile. And the alternative is a frequency-based mitigation where we just project out non-black body components using our multi-frequency data. And both of these gave consistent answers and negligible foreground biases in all the tests and sims and data that we did. Okay, and with that, we were ready to unblind this old ACT result. Here's the prediction. We got on a call. We had never seen the spectrum before, overplotted with the data, with the theory prediction, and that's sort of what we found. All right, so really nice agreement. And it's worth emphasizing, this black line is not a fit to this data set, right? This is a 0 parameter prediction. No nuisance parameters, just, compute what should it be and measure it. And it's pretty impressive given how much physics has to go right for this to work, right? They have to understand structure formation, lensing, predict the 4-point function. I measure it in a different experiment and it works. So, cosmology works pretty well. Okay, what does that mean for cosmological parameters? Well, usually what we constrain is in the sort of sigma 8 omega matter plane, just like all lensing measurements. You can see our direct measurement in combination with BAO to pin down omega matter here in red. It compares quite nicely to the sort of cosmic shear experiments analyzed in exactly the same way. And the headline result is sort of sigma 8 is 0.812 plus or minus 0.013. Yeah, it's a little unfair because we do particularly well when combining with BAO for reasons that I can talk about if people are interested. But yeah, the main takeaway is nice, this lensing is not low. We're just bang on consistent with Planck lambda CDM prediction from the point function. So, if you want to come up with new physics, it has to make this measurement agree with that one. Yes, so basically we have, yes, it's a banana otherwise, and you add BAO, and then it gets broken. The thing that's a bit odd is how well it gets broken. Maybe, well, I'll just briefly say it. If you just look at the two contours, it doesn't look like it would work that well, but it's because the CMB lensing constraint is like it's a line in this sort of omega matter H sigma 8 parameter space, and you're sort of cutting a line with a BAO plane, and that's different from weak lensing. So the higher dimensional, thinking about it in higher dimensions is needed to actually understand how it cuts so well. Okay, all right, let me now talk about the new results, all right, and what's upcoming. So I'll talk about the ACT SPT combined analysis, daytime analysis, and then what's going on with DR6 and SO. All right, so since the ACT papers came out in 2024, we've had another really nice lensing analysis led by the SPT collaboration and Feige and collaborators. And the nice thing about that analysis is that it was done with very, very different technology in a very, very different regime, right? So the SPT strategy is, the SPT 3G strategy so far has been to look at a really small patch compared to ACT at really, really great depth. And that means for lensing that your information is very much dominated by polarization. And it also means that you need to apply more complicated optimal lensing approaches. You can't get away with the quadratic estimator. People, Urosh and others have developed these over some time. And despite these very significant differences in how the lensing spectrum is measured, you find really nice agreement between SPT and ACT and Planck. So the ACT results are shown in red, the SPT ones are shown in blue, and the Planck ones are shown in yellow. Totally different experiments, totally different strategies, different observables, temperature versus polarization, and yet, they look pretty consistent. So that's pretty impressive. So motivated by this, Frank set out to do a combined analysis of all these three data sets. And computed the covariance, which is pretty much negligible between SPT and the other ones, and built a joint likelihood. So the first thing you can do is you can just derive a combined lensing spectrum, as shown here in black. Kind of cool. Signal to noise of 61. That's obviously much harder to do with something like cosmic shear, because you wouldn't have the same sources exactly. But here we just have one observable. We can just naively add them together. Sorry, was there a question? Yes, so there is, and we computed it, and it turned out to be really small. It's not surprising that it's small just because the SBT area is really little and compared to the ACT and especially the Planck area. So just from looking at the area, even if you assume on that area it's maximally correlated, you get sort of few percent correlations. And then it gets further decorrelated because you're using different scales, you have different noise, et cetera. So it actually ends up being negligible. Planck is all over the place. ACT is over a quarter of the sky. So, and SBT is, I think 1,000, what is it, 2,000 square? Forget. Yeah. That is let me talk about that in a second. That's sort of that's a power spectrum question. I think in ACT, we recently, after the lensing paper came out, had the power spectrum release. And you should ask, Sam Goldstein, for example, about some of the details there. But the A lens in both ACT and SBT was not, particularly large. It was a little bit higher, but it was not, 2 sigma higher. When you combine with Planck, it is still a little bit high, and maybe I'll get to that in a bit. Okay, so we had this nice combined Uber lensing spectrum, and there's also a combined likelihood, which we call the ACT-Planck SBT lensing likelihood, APS lensing. In the SBT paper, they called it SPA later, so we were grumpy, but APS. And right, so you can run constraints on this from this joint likelihood. First of all, the consistency that I talked about at the power spectrum level, of course, also shows up at the sigma 8 omega matter level, right? You can see the Planck only plus BAO, ACT only plus BAO, and then in blue, the SBT only plus BAO contours, agreeing really well, which is, as I said, amazing given how different they are in terms of their actual observables. Temperature versus polarization, small area versus large area. And then you can get the combined constraint, which looks pretty good. Sigma 8 is 0.829 plus or minus 0.009. That is, I think, a very impressive error bar. I do actually believe this result, more or less. I want to say it's the tightest measurement of sigma 8 until someone yells at me. And so far, no one's yelled at me, so I'm going to just keep doing that until someone does. Right, but yeah, again, the takeaway here is, consistency with lambda CDM predictions at high, very high precision. It is a little bit notable that it's shifted up a bit. That's in part because we're using a more extended range in ACT, and it seems to fluctuate a bit higher. Also, DESI BAO shifts things around a little bit, but not all that much. Okay, but prediction, quote unquote, and what you actually measure are really, really consistent. And the same sort of narrative to a large extent, but not a total extent, is true if you look at redshift-dependent growth with cross-correlations. So the idea here is something called CMB lensing tomography. And it allows you to track the growth of structure sigma 8, not in some large projection over redshifts, but in different tomographic redshift bins. So the idea here is if I have galaxy surveys, at least projected ones, they're limited. I can't determine sigma 8 from a projected tracer because I'm degenerate with the bias. But if I add a cross correlation, it breaks the degeneracy, and I can solve for sigma 8 in different redshift bins. And for a long time, a lot of these cross correlations with CMB lensing were coming in low compared to the predictions. The more recent ones and the more precise ones, the trend I think is less clear, and I would say arguably they're pretty consistent with what we predict from lambda CDM in terms of structure growth over time. So, there's some interesting regimes here. I want to emphasize sort of some, on the lower redshift side, some results from Garrett Farn, these tiny error bars that are hard to see in blue, very precise measurement of cross correlations of unwise galaxies with ACT and Planck lensing. And this really nice result from Noah Saylor and collaborators, which extends as of recently into this interesting dark energy dominated regime. There was some indication that maybe things were kind of dropping off from the prediction at low redshift, but the BGS sample is actually totally in concordance with what you would expect. Another interesting point about these cross correlations is the high redshift regime. So it's kind of, if you look at this plot here on the right, you see there's a data point at redshift 5.2 or something like that, 5.3. And that sounds a little bit crazy because we don't really have quasars or galaxies out there in any large numbers that we could do sort of cross-correlation science with. So the way this works is by combining the cross-correlations with the CMB lensing power spectrum. The CMB lensing power spectrum probes everything in an integral, all the way out to redshift 5, 6, 7, 8, 9, 10, but normally you can't isolate those high redshifts. But you can if you have cross-correlations, because the cross-correlations will pin down the structure amplitude at low redshift, and then combined with this integral let you solve for what's going on at high redshifts above where the galaxies are, or where the quasars are. And that's where this point comes from. Basically, this is from a joint analysis of cross-correlations with the lensing power spectrum, the structure that lies above where the quasars are. So, you know, this high redshift regime is not quite as unexplored as people may think. Yeah, so either galaxies or quasars. This one is correlated with quasars, but the quasars lie down here. Okay, so the quasar bins are here and here, but the CMB lensing is everything. And so effectively, you could think of it as I have a sum of these three, and then I subtract off this and that, and I solve for the amplitude here. So I have a projection over all redshifts, but I know from the cross correlations what's going on at lower redshifts, and I can solve for what's going on at really high redshifts. That's sort of indicated with this super wide range here. But you're right, it's a little bit, maybe slightly deceptive, yeah. Yeah, but yes, I think that the better way to think about it is this whole band, right? You're sort of, this is the midpoint of a whole range of redshifts, right? With the center. Yeah, exactly, yeah. That's the support of the sort of cross-correlation subtracted lensing, effectively, if you want to think about it that way. Okay, but generally, you know, I think the recent picture, and that hasn't been true for a long time from these cross-correlations, is generally mostly consistent with lambda CDM. Let me now start discussing things that maybe seem a little bit less consistent. And I think, obviously, as we heard from Dragan, the combination of CMB, CMB lensing, and DESI is not all that consistent, right? And this shows up in dark energy, especially if you combine with supernovae. But it also, you know, I think arguably shows up in lots of other extensions, right? The disagreement will drive those in different funny directions. So one thing that's a bit odd, as Dragan already indicated, is this really surprisingly tight constraint on neutrino mass, right? If you look at forecasts, it's frustrating because it's hard to motivate future experiments because these constraints are so good. They're so much better than they should be, right? And actually, this one is from DESI plus ACT, Planck, and SPT lensing. It's even tighter than the DESI one. So, you know, the inverted hierarchy, it's approaching 4 sigma being ruled out. So, and, you know, I think Dragan will kill me if I show this plot, but, you know, you can, if you don't take it too seriously, extend neutrino mass to negative values. Obviously, no one actually thinks the neutrino mass is negative, but you could sort of extend the effects it has to a minus sign and in various unphysical weird ways. And, you know, that is favored at between 3 or 4 sigma from the CMB-DESI combination, depending on how exactly you implement it. Right, so what is going on here? I mean, we heard from Dragan that, you know, some of it is driven by the matter discrepancy between CMB lensing versus DESI. One question, given what I showed earlier, that if I marginalize over lensing, these constraints blow up and I learn nothing. I thought it was, you know, I started thinking about, and I think lots of people have thought about, could there be a lensing problem? So I want to just take a different tack from what I've said so far, which has all been everything's consistent, there are no problems, and just think about maybe, you know, could there be a lensing problem? So it is true that if I look at the, you know, usual plot of omega matter H naught RD in disguise with slightly different units, I see that this is an SPT plot. The CMB versus DESI, they're sort of not in good agreement. But most extensions, or many extensions, allow them to come into concordance. And one of those extensions is A lens, right? So if I look at this line here, this is when I open up A lens, and you'll see allowing A lens to go to around 1.1 now suddenly everything is concordant. I think a large part of that is just because it allows the CMB and CMB lensing to go to lower values of omega matter and trade off A lens for lower omega matter. Yes? Oh, yes, that's a very good point. A lens is effectively a completely unphysical parameter that you rescale the amplitude of lensing with in both the power spectrum of the CMB and the lensing power spectrum. So it just says given lambda CDM parameters, for no reason whatsoever, lensing is higher by this factor. Okay. Now, also very unphysical thing. Were there any other comments? Okay, so there's no reason that would be the case, but it does bring things into better concordance. So, is there any reason to think that lensing might actually be a little bit high? And this might be driving some of the discrepancies. So, to play devil's advocate here against CMB lensing, maybe there is a little bit of evidence that lensing is a little bit high. And I think that's shown in this nice plot from this SPT paper by Fei-Ge. You might be wondering, how is this possible? Because you told us in the first half of the talk, everything is totally consistent. The lensing power spectrum is bang on what you predict from the primary CMB. The subtlety is that the primary CMB also has some lensing effect. So if you get rid of those, then it's high with respect to that lensing marginalized power cosmology. All right, so basically, to go into a bit more detail here, instead of just having one A lens parameter, the SPT folks, they introduce two. They have an A 2-point, which rescales the lensing in the CMB power spectrum, the 2-point spectrum, and an A reconstruction that rescales what I was talking about, the lensing power spectrum. And you can look at, so A recon, that tells you how the amplitude of this lensing power spectrum. If I look at the normal situation where I just predict the amplitude of lensing from the CMB power spectrum, and I say, okay, is my measurement of this reconstructed power spectrum high or low? The dashed line tells me totally consistent with 1. But if I marginalize over a 2-point, if I get rid of the lensing information in the 2-point function, the lambda CDM parameters I get have, I think, lower omega matter, and then they, relative to that cosmology, the reconstruction is a little bit high. So I think it's fair to say, in light of this, that maybe lensing is a little bit high at the kind of 2 sigma level. But I want to emphasize, this is probably the worst case scenario for emphasizing this effect. This is using PR3 and PR4. This effect will be reduced. If I use ACT, it'll be reduced, and SPT as well. But yeah, even though I've just emphasized total consistency, you could argue that maybe lensing is a little bit high compared to a lensing marginalized CMB power spectrum cosmology. Does that mean there's something wrong with lensing? I don't think so. Let me give some arguments. Some of them I've already made. The first one is lensing is generally pretty clean for the reasons I said earlier. And if you had foregrounds that you had misestimated, not mitigated properly, they would have the opposite effect. They wouldn't raise lensing, they would lower it. I talked about the fact that you have consistency between ACT, Planck, and SPT, temperature dominated versus polarization dominated, totally different techniques, totally different foreground sensitivity. Seems unlikely that would get messed up in the same way for all these experiments. Consistency of 2-point and 4-point is also non-trivial. These are, close to independent measurements. They're differently affected by systematic. So given all these consistency tests, I think it's unlikely that there's something wrong with lensing that's driving it. Maybe there's a fluctuation at the kind of 1.5 sigma level that's contributing to the DESI difference, and maybe even contributing to sigma 8 problems. But something to keep an eye on. Okay, maybe that's some more motivation for better lensing measurements, so we can figure out exactly what's going on. And that is coming up really soon in what's creatively called the DR6 plus lensing analysis. I wanted to call it DR7, but the bosses said no, so now it's called DR6 plus. What is the story with DR6 plus? When we did the DR6 lensing analysis, the one I talked about before, we were really careful to be robust, but we didn't care about being suboptimal. There was like a ton of, we didn't filter things optimally, we left a ton of data on the table, and now we're going back and we're trying to put everything in. So, we're doing more optimal filtering, we're improving the area, et cetera. And the biggest improvement, I would say, is the inclusion of the daytime data, which will almost double the amount of data. So Irene will talk about this on Monday. So I'm just going to sort of advertise some of her work. The idea of daytime lensing is that ACT and SO observe during both day and night. And it's a lot of time, a lot of effort, and they make maps of the daytime data, and then they just throw them in the bin, right? They just throw them away for lensing and for power spectra because they're worries about the beam and pointing. And these are not crazy. What happens is, the telescope during the day heats up, the mirrors distort, and you can sort of see the pointing solution going off on sort of hour time scales. Now, it's frustrating because if we could use this data, we would gain a factor of 2, right? Improvement, and in higher point functions, that doesn't mean a root 2 improvement necessarily. It can be a bigger improvement than that. Now, Irene will talk. Irene, this is a really hard problem. She did lots of great work, and I think basically solved the problem of how do I make this data usable for lensing, calibrating the day to night. Maybe she'll talk about the details here. Let me just say why this is not going to be really unreliable, right? You might think, lensing looks a lot like a beam distortion, right? So if I have a telescope that has beam problems, I'm not going to trust my lensing. This is a crazy thing to do. The reason I think it's not crazy is because of the timescales involved, right? So lensing would look like a really rapid beam distortion, right? It's sort of pretty small scales, degree scales, sub-degree scales. But if this telescope is warping over hours and it's scanning back and forth every minute, these slow distortions will project to huge lenses that we would throw away anyway and we would never want to measure. So all the problems should be confined to really, really huge lenses, and the things that we actually care about should be safe. And that's actually borne out by the tests that we can do. So what's cool about, the other reason I think this works is because we can do null tests that completely cancel the sample variance. So that you can be in a situation where your null test error bars are like 100 times smaller than your signal. Just because if I take a day map of the CMB and a night map of the CMB and I difference them, all the signal is gone. And my error bars on that difference, if you compare with the fiducial signal that's up here, are absolutely tiny. So you'd be able to find even a really small level of contamination. So anyway, Irene will talk about this. It's looking really good, and it will be one of the most important factors that will contribute to giving the DR6 plus lensing analysis a signal to noise that's above 60, approaching 70. And you can also do lensing spectra from daytime alone, day cross night. This will boost us significantly. And what's cool is if we can do this with ACT, which is kind of stuck together with tape, and it's not the best experiment compared to SO, we definitely can do it with SO. SO is much more carefully built. Like lots of thought has gone into the thermal stability. You can't tell the difference between the day and night beams. So if we can solve it for ACT, I think we can do it for SO. And that might mean that SO is a rare case of when forecasts that you do to get funding are pessimistic. So if you look at how well you can do for SO, and you do a forecast adding day data and making a few other improvements, we might be able to reach a signal to noise of 200 as opposed to like 100 and a bit that we thought we could do. And another reason to think that is that somehow advanced SO is ahead of schedule, which also never happens. Okay, let me then, since I'm on that topic, briefly talk about Simon's Observatory status before I spend 10 minutes on kSZ and hopefully finish somewhat on time. Simon's Observatory is the next generation ground-based CMB experiment. I'm sure most people in this audience have heard about SO. It consists of small aperture telescopes that focus on B-mode science. Those have been observing for a couple of years now. But what's new is that this large aperture telescope, which is what we care about for power spectra lensing SZ, that's been operating since February. And it's working surprisingly well. And we've actually been able to start to do lensing already, even though it's been a few months. So here is a lensing map from SO, which is pretty cool. This lensing map, which was made by Ola Kuszak, is derived from 144 hours of observations, which is not much at all. This is like almost no data from SO, but you can start measuring correlators like this one from 144 hours of observations. So this has like signal to noise of 14 or something. This is a correlation of lensing with CIB. And clearly this is non-zero. So clearly we have measured lensing, even though it's just, a week or less of observation. So, as someone who's old, I remember I spending years of my life getting things like this with ACTPol, and now you can do this in a few days or a week. So it's working really well. All right, in the last 10 minutes, hopefully, I want to talk about something somewhat different, which is kSZ and how it can tell us about primordial non-Gaussianity and sort of first steps in that direction. Are there any questions, though, or comments before I move on? Yeah.
Which sort of point to sigma equaling as at his paper. So how do you square those two facts? Was it different data used or what? It might have to do with this power spectrum and things.
Yeah, that's a good question. Yeah, it might have to do with, if I open up new degrees of freedom, then it could be, I don't know, I'd have to think about it. Yeah, it is worth thinking about. Obviously, the sigma 8 of z is not, there's some assumption, there's different choices in how you exactly extract that. It could be that some geometrical effects get mixed in. Yeah, but you're right. I think it's a really good question. I'm not sure. Maybe Sam, you've looked at this, right? Okay, yeah. Okay. Cool. Thanks, Sam. I mean, I think it's the same as what I was talking about earlier, right? It's a broad kernel that peaks at around redshift 2, but extends to really, really high redshifts. Redshift, even above redshift 1, yeah. 1 to 6, something like that. 0.5 to 6, yeah. But quite large scales, especially in the power spectrum. The peak smearing is very large scales, right? Larger than a lot of the CMB lensing power spectrum observables. Okay, I hope I can go 5 minutes over. Yeah, all right. Is that okay with the organizers if I go 5 minutes over? Okay, all right. Cool. Let me switch gears and talk about, instead of lensing, just for 10 minutes, I want to talk about the kSZ, the kinetic Sudnap-Zeldovich effect, and some. Okay. Okay. I always try. All right. The kSZ effect, I'm sure most people are familiar with, but just in case not, let me quickly review it. As the CMB photons travel through the universe, they're not just lensed, but they're also scattered. They're Thomson scattered by moving electrons in the cosmic web, okay? And the signal this produces in the CMB is then not just proportional to the electron density, but to the velocity field, the radial velocity field of the matter in our universe, which is pretty cool, right? We don't have that many ways of directly accessing the velocity field, especially at high redshifts above 0.1, 0.2. Now, it turns out, it's not obvious necessarily just because I have an effect that depends on the velocity field that I could actually recover a map of this velocity field or reconstruct it. But you can with a process called kSZ velocity reconstruction. And at least if I think about projected tracers, it looks really, really similar to CMB lensing reconstruction. So for CMB lensing reconstruction, we obtained a lensing map by looking at mode coupling between two different temperature modes. Here we obtain a velocity map by looking at mode coupling between a temperature mode and a galaxy survey mode. Okay, and that's not obvious why that will give me the velocity field, so let me just kind of try to explain why that should work with a few pictures. So the setup you should have in mind is, imagine a really sort of large scale radio velocity mode in the universe that you want to reconstruct. Okay, this is in this region of, in this direction, the velocity is negative, so it's going away from you, and here the velocity is positive, it's moving towards you. Okay? Now also imagine that I have galaxies that are kind of distributed in a sort of Poisson-like manner here. What do I predict for the CMB temperature map? Well, each galaxy will have some electrons associated with it, and those then get multiplied by the local value of the velocity. And so I'll get these blue dots here, where the velocity is moving away from me at the galaxy positions, and I'll get red dots over here where it's moving towards me. Okay, so this is the picture I actually measure in my CMB experiment, and I want to use that to reconstruct the velocity field. I want to solve, given this data and also this data, I want to solve for this. How do I do this? Well, what's done effectively is to measure a position-dependent cross-correlation between the temperature map and the galaxy positions. Okay, so on average, the temperature cross-correlated with the galaxies will be 0, because the velocity will be plus and minus in equal measure. But in this region, I will get a cross-correlation that's non-zero and has a negative sign. In this region, I will get a cross-correlation that is non-zero and has a positive sign. And so the sign, and in fact the amplitude of this position-dependent cross-correlation, tells me the value of the velocity field. And you can show that a position-dependent cross-correlation can be written in this way. It's just a convolution, basically. Okay, so that's how this works, and that allows me to reconstruct the velocity field given a CMB map and a galaxy survey. Now, I might not know the true cross-correlation, right? Which involves knowing the correlation of the electrons in the CMB with the galaxy. So there's some unknown electron-galaxy cross-correlation. But on large scales, that just shows up as an unknown bias factor, just like in galaxy biasing, like a constant bias factor multiplying the reconstructed velocity. So I assume some fiducial galaxy electron cross-correlation to measure this position-dependent power spectrum with, but if I get it wrong, it just gives me a constant overall factor multiplying this velocity. Okay, so we have a velocity field. We can easily convert it to a density field, right? Just on large scales, I can just apply the continuity equation. And you'll note that, of course, there's some powers of k involved in this filtering. So from this velocity, if I want to solve for delta m, this velocity is a really bad probe of small scales, because there's a power of k multiplying the noise. But it's a really good probe of large scales, one of our best probes of the really, really large scale modes because of this k filtering. And as a cosmologist, if you're presented with a really amazing probe of large scale modes, you immediately think of constraining primordial non-Gaussianity, right? Because you all know why primordial non-Gaussianity is interesting, can tell us if single field inflation is right or not, et cetera. I think this audience knows all about it. And you also know that one of the best ways that we have of looking for FNL, for non-Gaussianity, for local non-Gaussianity at least, is via the scale-dependent bias, which is an excess, which shows up as an excess in the power spectrum on very large scales. Okay? But you also probably know that this is very hard. Measuring FNL from galaxy surveys is very hard, and there are two reasons that it's hard. One of them is just there are not many modes on large scales. So sample variance is large, error bars are big. The second, and I think scarier issue, is that lots of things, lots of systematics generate excess power on large scales, lots of observational systematics. And the scary scenario is that you find some excess and you make a big deal out of it, and it turns out, okay, it's stellar contamination or variations in depth or something like that. I think it would be very, I don't know, maybe others disagree with this, and there's been a lot of progress on mitigating these systematics, but I would find it hard, it'd be hard to convince me definitively that we found something and it's not some excess junk. Because if you just take a galaxy survey, you measure a power spectrum, you'll see some huge excess in junk at low K. So I think a really nice way of solving, especially the systematics problem, is to add a new tracer that's either clean or at least independent of the galaxy tracer. Now, this can also solve the sample variance problem via sample variance cancellation, like Urash and others described. But I think what's particularly exciting is just if we could only use cross correlations to measure FNL, and if we saw FNL without using any autocorrelation information, I would really believe it. I think at least I would believe it more. So CMB lensing is one option for an independent field that we can cross-correlate with, and there have been lots of analyses where FNL has been measured from cross-correlating CMB lensing with a galaxy survey and constraining the scale-dependent bias. And that works extremely well in the sense of mitigating systematics, right? So, you can take, as an example, the most contaminated tracer I can think of on large scales, which is the CMB, which is just buried under orders of magnitude in dust. And in cross-correlation, you can make it work. You can get really nice constraints on FNL. This is a paper from Fiona McCarthy. I forgot the citations. And we're working with a student to actually make this a factor of 2 or more, or something like that better. Now, if you add the autocorrelation, this can be pushed really far. Urash and Marcel Schmidtful showed this. If you just want to use cross-correlations, in the forecast that I run, it seems hard to reach errors of order 1 from only cross-correlation information if I can't do the sample variance cancellation fully. The kSZ is nice, though, because it's 3-dimensional, right? So instead of having one big projected tracer where I need full sample variance cancellation, I can have tracers in every redshift bin, and I can just use cross-correlations to measure FNL. And so I think the original case for doing velocity reconstruction was we're going to do a ton of sample variance cancellation, and it's going to improve the already amazing constraints on FNL by factors of several. I personally am more excited about the systematics reduction case, right? If we can measure FNL with no autocorrelation information, just from cross correlations, and it's still pretty good, right? The constraints, like if I take LSST and I throw away L of 100 and below in the autocorrelation, I can still get to FNL below 2 from kSZ cross correlation. So I think that would be really nice, and I think I would really believe something if I see it in kSZ cross correlations. Okay, but this so far until last year, this had all been forecasts, right? People had written theory papers and forecast papers, but no one had actually measured the signal, and that's what Fiona set out to do. Okay, so she took the ACT data and the DESI photometric LRG sample and built this quadratic estimator. This was sort of a projected binned estimator, and measured for the first time, at pretty low significance and with lots of noise. This is mostly noise, but under the noise, there's some real velocity information telling you about how fast the matter is moving in different directions, and in 4 different redshift bins. Now, just to quantify the measurement significance, you can correlate it with boss galaxies, and again, this is the first time this has been done, and she sees something that's non-zero at around 4 sigma. So that was last year. Not all that convincing if you look at the actual measurement, but with better galaxy data this year, like the same velocity map gives you around a signal to noise of 10. So it was detected last year. Now the measurements have reached a signal to noise of 10. And I think that's pretty clearly non-zero. There's also, in addition to Fiona's work, after Fiona's work, there were other really nice analyses by Alex Lagou and then Anderson Lai. And I think the recent one from Salim Hotinli that I want to highlight, which I think is really cool, because they used a measurement of kSZ in cross correlation, also with a signal to noise around 10, to actually get some pretty good FNL constraints. So I think the constraint is around plus or minus 40. Now that doesn't sound all that impressive compared to Planck, but literally we had not seen the signal and we're not able to detect it until last year, and we're already getting constraints of around plus or minus 40. So, I think that's pretty impressive progress. Now, having said that, and having said that there's great potential for getting FNL of order 1 just from cross correlations, I think it's worth emphasizing there's a lot that we need to do, right? I think, for example, foreground systematics, there are reasons to think they're small. They're sort of parity arguments. But when we actually looked at this in the data, there was some evidence that they were not totally negligible. Higher order. Yeah, so basically the velocity reconstruction involves a TG correlation. Then you correlate with another galaxy field. So you have this TGG bispectrum. But if the T map has some like SZ in it or CIB, I can have this like CIB SZ correlator in it. Because of parity reasons though, it's suppressed a lot, but it might not be like completely zero. But I think it's not a big deal. We might have to just do some multi-frequency cleaning, but it's very small. But yeah, we just don't know. Higher order effects. Kendrick Smith and collaborators started to look at these. We don't have them for projected tracers yet. Galaxy systematics. Obviously, it's going to help to do this cross correlation. Like if I have some, additive systematic that doesn't correlate with CMB temperature, that's going to disappear. Stellar contamination probably will be gone. Maybe you'd have to worry about galactic foregrounds in the temperature map correlating with extinction in the galaxy survey or something like that. Yeah, we need to just make sure quite how small and the systematics are even after this cross correlation. But I think it'll certainly help. And this is a topic of ongoing research. All right, so I'll leave you with my summary and thanks for your attention. Questions? Right. So yeah. They're both really the same bispectrum, but looked at in different limits. So the way the kSZ, the way you detect these electron profiles is that you take the velocity field from the continuity equation, right? So you assume that I have the density field. I can divide by some fiducial bias, apply the K filtering, and then I do the stack on that, right? But what you get out of this is the profile, right? But it is true that it's a similar bispectrum, and it just looked at it in a different limit. And it would be nice, and there the uncertainty in the velocity field, yeah. So effectively, you're measuring the same bispectrum, but you're interested in different sort of reconstructing different sort of parts of this bispectrum. You're looking at different limits. Yep. Yeah, I think, I see. So you're saying it's like the same bispectrum detecting. I'm not sure, I'm not sure it's actually, well, I think it is, like, for example, the velocity fields, yeah, maybe I'd have to think about that a little bit. I think it's certainly true that if there was no real velocity field, I would not see the stack, right? There would not be a real velocity weighted stack. Obviously, so I think in some sense it's the same bispectrum and it's related information. It's just a sort of different limit of the same bispectrum, and I'm not sure they're highly correlated. So it's the same as in this is also the photometric sample in both cases for DESI LRG. So it is very similar to like Boyana's analysis for the velocity. Yeah. I mean, ultimately, I think it would be hard to get FNL. I think it's the same bispectrum seen in a different limit. I don't think you're going to get FNL from this kind of thing. I think what would be very exciting, actually, though, is combining. As you say, these are closely related quantities, right? You're measuring a TGG bispectrum in disguise in sort of different limits. It would be nice to connect the two because the uncertainty that we have here, this unknown galaxy electron cross correlation, is like closely related to what Boreana measures. So you could do a full joint bispectrum analysis in these different limits, right? Where here it's sort of squeezed in one sense, and you might both learn about the velocity field and the baryon properties. But yeah, it's a good question how to relate these two, and I'm not sure. I'd have to think about it a little bit more.
Aren't you working against the fact that power spectrum, the quantity measured, not what is one over FNL is 1/k, not 1/k squared? Or is it still 1/k squared because
Yeah, it's 1/k, so that's true. So you have, I mean, it's roughly like a factor of 2 less sensitive, right? So or something like that. Yeah. So I think you are losing that. Yeah. So the velocity will not depend on. Yeah, but if I compared with a systematics-free LSST gold sample, going to the same L, like it's just that you can push. Like it is true that you lose constraining power by, having bigger error bars, and you lose constraining power by, having like losing a factor of 2 for the reason you said. But then it's so steep that if I can go to lower L min, it's pretty easy to kind of compensate that, at least in part. Between B and delta. Oh, V and delta. Yes. So, could you basically measure the growth rate or something like that? Is that what you're thinking about? Yeah, I think actually Nick Battaglia is working on a paper, I think, along these lines. I think, but yeah, could do this. I mean, one issue, I guess, with that kind of stuff is like scale-dependent bias is nice because it's a feature that's not degenerate with just an overall unknown factor. Like, FAH and this sort of tau degeneracy, those are probably going to be, so I think you could probably do this if you have some information about the baryon properties, but worth thinking about. Yeah, so in principle, if you're allowed to split your data into more splits, then you can recover all the information, right? So there's the number of splits you use, as that goes to infinity, you get 100% of the information. But with 4 splits, you're right, we are losing some. It's around 10%. So that was one of the sort of 10% factors that we could probably improve. One of the main reasons it's so little is just like in ACT, we're still dominated by temperature information. And we're signal dominated. We do an L cut because of foreground control reasons. And so just increasing the noise a little bit, like it actually doesn't really hurt our lensing reconstruction, which is sort of sample variance dominated. The polarization gets a bigger hit though. Yeah. Yeah, so I think we might try to add more splits. It just, the cost is just computational time. And we need to have the splits in the first place. Sometimes pixels are not scanned that many times. Yeah, exactly. That's the statement. So, in a super hand wavy way, you could say the 2-point information has some lensing source of information and some non-lensing source kind of averaged together, and the 4-point is consistent with that. But if I get rid of the lensing information, the parameters are such that it's a little bit high, but it's not that much. Yeah, yeah, you could have, I guess it would be, probably hard maybe to do that. Yeah. I mean, right. I guess it's a general question of can I boost? Well, I don't know if you want to keep GR and then I have to boost structure growth. It's not super trivial. Like a bit more CMB lensing. Yeah, possibly. I don't know. Yeah, probably be hard to do. I guess the other thing that's a bit weird is you'd have to like turn structure higher and then it would have to go down again to match other lower redshift probes if you're not just boosting the lens. Yeah. All right.